This is IB Math AAHL Week 4. In the past 4 weeks, we've learned about, well, not the past 4 weeks, but the past like week and a half, we've learned about the binomial theorem and different kinds of proofs in math. And we're gonna start by learning the binomial theorem. So before we start with the binomial theorem formula, we have to start with permutations and choose. We have to know what that is. And we're going to first learn permutations. And I think the best way to learn that is just from a word problem. And what a permutation is the number of ways a set can be arranged. And the order of the set does matter in this case. So here you can see the thing says you have letters A, B, C, D, and E, and want to find the number of arrangements for 3 of these letters. So I've kind of already drawn here one of the arrangements. Not, I haven't drawn the entire thing because it'll take a while, but what this is saying, it was you have 5 letters, and you can arrange them like, well, you can arrange it if you start with A, you can go A, B, C, D, and E, or you can go A, B, C, E, D, then A, B, E, C, D, and so on. I think you understand. And you can keep on doing that. You can do this whole thing 5 times. You could start with B and then C and then D and then E. And if you write this whole thing out for A, you'll find that there's 24 different combinations. And it says that you want to find the arrangements for just 3 of these. So if you imagine, we want to find the arrangements when it switches, we could say A, B, and C, just 3 of them. And so how you do it is, well, if you actually wanted to just find the number of arrangements, not for just 3 of them, just for all of them, you do 5 factorial because you have 5 different letters, which is equal to 5 times 4 times 3 times 2 times 1. But since you only want to find it for 3 of the letters, what you do is you want to get the number so it stops at 3. You want to get it so it's just 5 times 4 times 3. So you have 2 times 1 there. And this 5 times 4 times 3 times 2 times 1 over 2 times 1 is, well, it's 5 times 4 times 3. But it's also 5 factorial over 5 minus 3 factorial. And notice how we have the 3 here and the 3 there. That's because we have a value r equals 3. It'll come up in when I write the actual equation. But r is the term number that we're given. So 5 factorial over 5 minus 3 factorial is the same as 5 times 4 times 3 times 2 times 1 over 2 times 1. And you can see from this equation right here that you can write it like this. If you say n is the number of the total number of arrangements you have, or n is the total number of letters, in this case letters, we have A, B, C, D, E. N is n minus r. R was what I said before, the term number that we have. So this is the equation for a permutation. This is the number of arrangements that we have. And if we didn't want r to be anything, we just wanted the number like 5 times 4 times 3 times 2 times 1. If we just wanted that, it would still work. In that case, r would be equal to 5 because we want all 5 combinations. And so you'd have 5 minus 5 factorial which equals 0 factorial, but 0 factorial is actually equal to 1. So you'd have 5 factorial over 1, which equals 120. So this works for anything. The combinations that you want is R. We wanted 3, so R was 3. If we wanted 4, R would be 4, and so on. That's what a permutation is. And but with there's one more term which is choose, the one that I said before, and I'll just briefly go over this. Also permutation is written like this. Yeah, just to briefly mention that. NPR. Anyways, let's get rid of that. Choose is just the number of ways here. The number of ways when the order isn't important. When it's not important. For permutation, the order is important. For choose, it's not. That all objects um can be chosen. The arrangement, how it can be chosen, it's kind of hard to explain. I know, but the way that you write it is NCR equals. It's very similar to the permutation equation. It's just with an R factorial. And I accidentally wrote 3 either. I meant to do R. Very similar. N minus R factorial times R factorial. That's choose. Now we can move on to the actual binomial theorem. Now that we know that what choose and permutation is. And I also forgot to mention NCR. In the binomial theorem, some textbooks have it like this, some textbooks don't. It'll be different, but it might be written as NR like this. It's the same thing, and this one is the one I'm gonna use for the binomial theorem, but they mean the exact same. And now we can move on to the binomial theorem formula. So here's the binomial theorem, and this might look a little weird at first, but you only have to remember 3 things. That this NR is that choose thing we were doing earlier, and choose is the number of ways of choosing R objects from n distinct objects when the order isn't important. You also have to remember that this just equals the sum or summation. And finally, that this whole theorem, this whole binomial theorem is just a way of expanding a, b to the n. We all know how to expand a plus b squared, which is just a squared plus 2ab plus b squared. But what if it's like n to the 1,000, right? It's gonna be super hard. And the binomial theorem just makes it a little easier. So if you were given a problem, and I'm gonna erase all this, and it wanted you to expand 2 plus 3, it wanted you to expand it to the let's say fourth term when r equals 4. Well, you just plug it in to the summation 5 r. We start r from 0. That's the standard way of starting the where you start from. It's from the first term. And then you have 5 4 a, which in this case a is 2. So um you put, sorry, my mic turned off for a second. You put 2 there. 5 minus 4 b. I don't know why I keep writing the letter. B is just 3. So you have 3 4. And then you can solve this. Okay. So since the summation thing, this just means summation, you can actually, and I was like super happy when I found this out in class, you can actually just kind of forget about it. You can just write this as 5, 4, 2 to the 1 times 3 to the 4th. And now the equation is a bit more simple because you know what that 5 and 4 thing is. And then you know what 2 to the 1 is, which is 2, and 3 to the 4, which is 81. That's 81. So let's write now what 5, 4 is. Well, from the choose formula, which we had before, which is choose equals n factorial over r factorial n minus r factorial, we can say that this is 5 factorial over 4 factorial 5 minus 4 factorial, which is 1 factorial, and 1 factorial is just 1, so you have 5 factorial over 4, and this is equal to 5 times 4 factorial over 4 factorial. Those cancel out, so then you just have 5. You just have 5 left, so you'll bring it back over here. 5 times 2 to the 1 times 3 to the 4. And like I said before, 3 to the 4 is 81. So what you really have is 5 times 2 times 81. And if we put that into a calculator, we're gonna get the answer to be 810. 10 times 81. And now we've solved it for when we want r to be 4, when we want the fourth term number, it's 810. That's the summation of it. Because remember, we have the sigma here. This is the sigma over here for summation. The answer is 810. Now we have proofs. So for proofs, there's 4 different kinds of proofs in math. There's deduction, induction, contradiction, and counterexample. Um, After I explain these, I'm not gonna go over every single one like an example problem because that will take a long time, but I will for one of them. Anyways, deduction is you're given a statement and you have to prove that statement, the general statement for a particular statement. For induction, you have a particular statement and you have to prove it for all general statements. That's why deduction goes from general to particular. Induction goes from particular to general. Contradiction is when you take an inverse statement and you prove you prove or you disprove that, sorry. You try to disprove the inverse statement so that if you're able to disprove it, then that must be the original statement is true. And counterexample this is actually not a proof, this is a disproof. If you have a statement, a counterexample is just disproving it. That's all it is. Okay, despite what I said before, I'll actually do 2 kinds of proofs, induction and contradiction. For deduction and counterexample, deduction is probably the easiest one, so you should be able to find online how to do that. And counterexample, it's a bit hard to explain because you kind of also just have to use some guessing and checking for that one. So induction and contradiction are the ones that I'm gonna do. And I'll start with induction. So you're given the statement that says prove that the sum of Pn is true for any n where n is any positive integer. And you're given the equation that Pn equals n times n plus 1 divided by 2. This is a pretty standard problem. This it's it's used a lot for the examples of how to do induction. So when you're doing induction, the first thing you want to do is you want to prove that um, this statement is true for the base case. And what I mean by the base case is you want to prove that it's true for 1. So you'll have Pn equals 1 plus 1 plus 1 divided by 2. Or sorry, not 1 plus 1 plus 1. 1 times times. And you just do this out. You get 2. 1 plus 1 equals 2 times 1 equals 2. And so then 2 divided by 2 equals 1. So we've proven that it works for the base case. That's the first step. The second step is to assume that Pn is true for like whatever n is. So like let's say n equals k. We want to assume that it's true. So assume Pn is true. Okay, we can assume that this is true because we've proven that, well, let's say, when we had n equals 1, and this was true. So now we can assume that Pn is true for any n equals k. And since we proved that it's true for 1, we can move on to step 3, which is prove that k that p k plus 1 is true. And the reason that we're doing this, it might be confusing to have n equals k. You're switching the variables. Honestly, I don't think you really need to, but most textbooks and teachers will have you do this just so you can kind of separate them. But what this statement is really just saying, I mean, it's also can be n plus 1, but they have the plus 1 because since n is any positive integer, you go from 1 to 2 to 3, you're adding 1. So if we can prove that p k plus 1 is true, then we can assume for any case of n, whatever it equals, that it's true. So if we can prove it's true for 4, p4, then it must be true for p5. That's what we're going to prove with this. And I'll erase all of this so we have some more space. Sorry, I think my mic turned off. But well, I think we were at this part where we're just trying to prove that it's true. And I think I explained why we're trying to prove that that p times p k plus 1 is true. So here's how you'd start this. You want to write out the series that um since the original statement was that the sum of Pn, let's start by writing out uh pk plus 1, and let's write out the sum, the series that we can get from it. We can get 1 plus 2 plus 3 plus 4, and this will go all the way on to k, whatever k is. And since we have k plus 1, it'll go a step further, and it'll be plus k plus 1. Now, in the previous statement, what we assumed was that this part of the equation, because we proved the base case of p plus 1, so we were assuming that this part is true and that this part is k plus 1 divided by 2, which was the original thing, which I'll actually put up here, what we're trying to prove again. So That's what we that's what we're assuming is true. And from there, now that we have the k plus 1, well, since it's plus k plus 1, that we could do this. We write it like that. And we want to combine the equation into one thing. So the way to do that is to multiply k plus 1 times 2 so we can get the same denominator. So we'll have k times k plus 1 divided by 2 plus 2k plus 1 divided by 2. And this will simplify, and since we have two k plus 1s, this will change into k plus 2 because we have the 2 from there, times k plus 1. The k plus 1 was something that we factored out over 2. And so from here, this is how you can, we're gonna change the equation again into this. We're gonna separate this 2 right here into k plus 1 plus 1. And the reason that we're doing that is because if we go back to the original equation where we had n plus 1, we want to get inside the parentheses that plus 1. And then outside, we're going to leave this k plus 1. So hopefully it'll be easier to see once I write it out. K plus 1 times k plus 1 plus 1. Right? And sorry, that doesn't look like a 1. I accidentally drew another second parentheses right there. And we have all of that over 2. And now it's solved. You since the equation is like the one we have up top, right? Up there. We have proven that when we plug in k plus 1 into n in this equation up top, that you that it works, that you get this equation down here. Now we have proof by contradiction. So we have this statement that prove square root 3 is irrational. And since it's a proof by contradiction, we're going to assume that square root 3 is rational. That's what you do in a contradiction. You assume the inverse statement. And how we start this is, since square root 3 is rational, that means we're assuming that it is. We can say that square root 3 is equal to m over n, where m and n belong to some integer and have no common factors. Common factors. Okay. And they have no common factors because that's what a rational fraction is. It has no common factors. So let's move on. Since square root 3 equals m over n, we can say that square root 3 squared equals m squared over n squared, which means that 3 equals m squared over n squared. And so we can say that 3n squared equals m squared. And now we can divide 3 on both sides to get n squared equals m squared over 3. And now this is very interesting because let's just look at the m squared over 3 for a second. Another way of writing that is m over 3 times m. So because we have this m over 3, we're saying that m is divisible by 3. So m is a multiple of 3. I'll write that here. M equals multiple of 3. So now that we know that m is a multiple of 3, we can say that m equals 3, and we'll just say k, 3k, whatever k is, 1, 2, whatever. And this is true because, like I said, m is a multiple of 3. So now that we have m equals 3k, we can plug that back into the equation. And actually, let me just specify that k equals any integer. It's important to specify in these proofs. But we'll plug that back in. So m squared is going to equal 3, sorry, not 3, 9k squared. So then we'll have 9k squared over, or sorry, not over, we'll have 9k squared equals to 3n squared. And now we can divide by 3. So we're going to have 3k squared equals n squared. But this looks very similar to how we just proved that m is a multiple of 3, right? Because now we can divide 3, n by 3, n squared by 3, sorry. And now we can say that n, like we said for m, is a multiple of 3. Let's say if n equals 3x, right? So n is a multiple of 3, and m is a multiple of 3, which means that they have a common factor of 3. But as we have up here, because it's a rational number, they're supposed to have no common factors. But they do, which is 3. So since m and n have a common factor of 3, then it's not a rational number. So we've just disproved the contradiction, which was that square root 3 is a rational number. So now that we've disproven that square root 3 is a rational number, we've proven that square root 3 is an irrational number.